Good morning YouTube, and welcome to my next worked exam answer video, where today we're going to have a look at two different Arrhenius questions. With the Arrhenius equation, there are two things they may ask you to do. They may ask you to rearrange the equation to work out the activation energy, which is what the second question here is going to get us to do. Or they might ask you to take this version of the Arrhenius equation and plot it graphically, and then use the graph to work out the activation energy. Now they've already plotted the data for us here, and it might be the questions ask you to plot the data, but that is basic graphing skills. What we need to be able to understand is how from this particular graph, where we have ln k and 1 over t on the axes, can we get the activation energy. So I thought I'd show you both of these types of questions, because from the evidence that exists so far, when asked about the Arrhenius equation, these are the two different skill sets we need to have. We need to be able to work with it graphically, and we need to be able to rearrange it to calculate unknown values. So in this video, that's exactly what I'm going to show you how to do. So the Arrhenius equation can be written in this form: ln k is equal to minus EA over RT plus the ln of A. Now, if I want to plot this equation on a graph, I need to match up the different parts of the Arrhenius equation to the equation of a straight line graph, which is y is equal to mx plus c, where m is the gradient and c is the y-axis intercept, and x and y are what we plot on the x and y axes respectively. So by writing out that equation for a straight line, I've then colour coordinated what we would then be plotting on the y-axis, what we end up plotting on the x-axis, and what that means the y-axis intercept and the gradient would be. Now in this particular question, they have told you, or they've shown you on the graph, that ln k goes on the y-axis and 1 over the temperature goes on the x-axis. In nearly every single question that exists where you are dealing with the Arrhenius equation in a graphical format, you will be told which of these two variables to plot on which axes, or they would have labelled one of the axes for you, so it is clear. There is only one question where neither axis is labelled, and you have to remember that it is ln k on the y versus 1 over t on the x. So it's worth remembering in case they don't give you that information, but the really key thing here is we are interested in getting the gradient of this line. And the reason why we're interested in getting the gradient is because all of these graphical questions all ask for the same thing. They all say, use the figure above or use your graph to calculate a value for the activation energy in kilojoules per mole. And going back up here, the activation energy comes under the gradient part of my y equals mx plus c. So I have to get the gradient, and then I'm going to rearrange that to get what the activation energy is. So you have to remember this. If you don't remember anything else about the Arrhenius equation, remember this. And then what we need to do in this question is work out the gradient of this line, which I'll do in a second. And we then need to rearrange this to get activation energy. So activation energy will be equal to the gradient times by minus the gas constant to get rid of the negative here. That will then come out in joules per mole. And the other key thing you have to remember here is that the activation energy will always come out in joules per mole, and they will always ask for it in kilojoules per mole. Obviously always worth checking that they will, but evidence shows that they always ask for it in kilojoules per mole. So to go from joules per mole to kilojoules per mole, we are just going to divide by 1,000, and that will give us our final answer. So let me get the gradient of the line, let me sub those numbers in, let me show you the final answer. And then of course, if anybody has any questions, they are more than welcome to get in touch with me by leaving a comment on this video or reaching out through one of my social media platforms. Okay, so in order to work out the gradient of the line, I have chosen 2 points where the line crosses very clearly through the grid points, making it very easy for me to work out what those values are on the axes. And I did the same thing up here. And the gradient of the line is equal to the change in the y-axis values divided by the change in the x-axis values. So just take care with the y-axis, because when we take the natural logs, the ln's of the rate constant values, they come out as negative numbers. So the scale starts at 0 at the top and gets more negative as we go down. So just be careful reading off the scale. So we've got minus 3.2 here and then we've got minus 13 here, and then on the x-axis 0.0013 and 0.00175. And I've put those into my change in y over my change in x, and I get minus 21,777.7. It's negative, we can see the gradient is negative, which is a good thing, but that also means when we then plug it in here that we're going to get a positive value for the activation energy, which of course makes logistical sense. So now that we've got the gradient, I can times that by minus the gas constant, and that gives me the activation energy in joules per mole. And then all I need to do to get it into kilojoules per mole is divide it by 1,000. And to three significant figures, the answer is 181 kilojoules per mole. Now, one of the things that I really like about AQA is that they will give you lots of method marks, even if your gradient is wrong. So heaven forbid you work out the gradient of the line incorrectly and your answer lies outside of the range that they will provide for the gradient. You don't have to get the value smack on. I'm not 100% in Q with the mark scheme, but I'm within the range, so that's fine. They'll give you a mark for that, but if your gradient is wrong, then you can still get the mark for doing whatever you get for your gradient, times by the gas constant, times by -1, or times by minus the gas constant to get the value for the activation energy in joules per mole. And then you can also get a mark for doing whatever answer you get here and dividing it by 1,000 to convert it into kilojoules per mole. So even with an incorrect gradient, you can still get 2 of the 3 marks here. And likewise, if you were having to plot these points yourselves from a table and then do your line of best fit and then get your gradient, again, if you plot your points wrong, but you get your line of best fit based on your points, they're happy with that. Then, so long as you're using your line of best fit to get the gradient, again, you will get lots of method marks moving forwards. Now, as I said at the beginning, they never mention that to work out the activation energy, you need to find the gradient of the line. So you have to remember this bit in the pink box, okay? It's also well worth remembering what gets plotted onto each axis, even though, like I say, in all but one of the questions that exist, they have given you some sort of clue in the body of the question or on the graph itself what you are plotting on each axis. But again, I would probably just learn that lnk goes on y and 1/t goes on x. And that is one type of Arrhenius equation question you might get in an exam situation. Now let's have a look at another one. So here is the next one, and you can see that the Arrhenius equation has been given in a different format here. There's 2 ways we can represent the Arrhenius equation, this way and the way that you saw on the other side of the page. Now again, all of the evidence that we have so far suggests that they will give you the correct equation for the job. So we can use this form of the Arrhenius equation here, and that's why they've given us it in this format. Whenever we're doing graphical work, we need it in this format. So anytime there's a graph question, they will give you it as lnk equals minus EA over RT add ln A. Whereas here, we don't need it in the other format, so they've given us it as K equals A e to the power of minus EA over RT, where E is a mathematical constant and a button on our calculator. Now in this question, they're getting us to do a little bit of rearranging to calculate a value for the Arrhenius constant A, which is the capital A in front of the E. We've been given a temperature, albeit in the wrong units, a value for the gas for the rate constant K. We have also got the gas constant R, and they've given us the activation energy, again, albeit in the wrong units. So some of the marks here are going to come from converting the units, some are going to come from rearranging the equation, some are going to come from getting the right answer for A, and some are going to come for giving the right units for A. So let me do some highlighting, some unit conversions, some rearranging, subbing some numbers in, and then I'll come back and explain my final answer. Okay, so the first thing that I always do with calculations, which you'll know if you've watched these videos before, is I always do my unit conversions before I dive into the main body of the question. So I've converted my temperature from degrees C into Kelvin by adding 273 to get 298K. And then my activation energy needs to be in joules per mole, so I need to multiply 96.2 by 1,000 to get 96,200. Then, to get a value for the Arrhenius constant, I'm going to need to rearrange the K equals AE to the power of minus EA over RT. So A is going to be equal to the rate constant K divided by E to the power of all of this. And then I've subbed my numbers in. Now, in terms of E on your calculator, it is the little symbol above the LN button. So LN and E are mathematical opposites of each other. So in order to get the E, we're just going to go Shift and then press the LM button, and you get the E on the calculator. And then you can turn that little box into a fraction, which is what I did. And then I subbed in the numbers for the activation energy, minus 96 to 100, and then divided it by the gas constant, 8.31, times by the temperature, 298. And then I pressed equals on my calculator, and then I did the rate constant divided by my answer, and it gave me this. Now we should always think about the number of significant figures we're going to give our answers to, which for me here is going to be 3, so 2.57, and I chose to put it in standard form, times 10 to the minus 9, because I just feel like writing 257,000,000,000 feels a bit wrong to me personally. You don't have to put it in standard form, the question hasn't demanded standard form, they'll just be interested in your significant figures. Now in terms of the units for activation energy in joules per mole cancel with the units for the gas constant in joules per Kelvin per mole and temperature in Kelvin. So all those units disappear, and therefore the units for A have to match whatever the units for the rate constant K are. Now we know from the rest of this topic that the units of the rate constant will change depending on the rate equation, but we've been given the units for the rate constant there as seconds to the minus 1, so therefore the units of A here also has to be seconds to the minus 1. And that's the other type of Arrhenius equation question they might ask you. If anyone has any queries about either this question with the rearrangement or the graphical one over leaf, please do not hesitate, like I say, to drop me a comment on the video or reach out via email or any of my other social media platforms. Thank you so much for watching. I hope this has been helpful, and I hope to see you again soon.